Got a Clodo. Yep, the ecosystem services part of this project was a seed funding project, so is a little bit different to the others in that it didn't aim to deliver a region-wide map output, but instead to think through some of the implications and some of the potential uses of data layers that have come out of the rest of the program, particularly Jan's vegetation layers that he's just showed us. Ecosystem services are these amazing benefits that people get from nature. A more modern, there's a lot of words for this kind of thing, but nowadays people are talking about nature's contributions to people instead. But it's all the same kind of idea, and there are generally 3 or 4 types of these ecosystem services, ranging from things that we consume directly, like food produced in farmland, to functions of ecosystems that regulate the environment, like we heard, for example, about erosion control earlier, or the way that trees store and sequester carbon. And then there are the cultural values associated with ecosystems, like recreational benefits and so on. So there's quite a whole range of these things, and in this program we didn't look at all of them. Ecosystem service models have been developed now for maybe 30 or 40 years. There are a few big global platforms that have been developed by different universities and things. They either rely on field data sets, which are really brilliantly detailed, but quite time consuming and expensive to collect, and so not very scalable. Or in some cases, they're derived from quite coarse data sets. For example, you might have a map of forest versus grassland. So the promise of LiDAR is to give us higher resolution information in 2 ways. First is the improvement in spatial resolution, so more detail there. But also we hope to be able to get more information about the structural characteristics of the vegetation itself. For example, Jan was talking about the height of the trees, and this should help to move us towards more mechanistic models of how these different ecosystem services are actually provided. So we aimed to come up with a way of fusing the LiDAR information with all of the other data sets that are available for New Zealand to parameterize some ecosystem service models, and to write this up as a set of software functions, in this case using the R language, to make ecosystem service analysis a bit easier, but also to make it more easily repeatable in the future if there are updated data layers, but also even just across the different regions of New Zealand. So instead of a set of map outputs, the main output for this is the R package and its documentation. And there are also some maps as well for a smaller test region. The scope in terms of the ecosystem services to look at was these 7. So we made, some of these have more than one indicator or method or model in the R package, but they are the role of ecosystems in retaining nutrients, the role of mostly tree leaves in absorbing particulate matter air pollution, the carbon stocks, not quite yet the sequestration, but the stocks that are held in above ground biomass, the role of vegetation and soils in retaining runoff, the role of trees in providing shade. Closely related to that one is the role of the canopy in providing ultraviolet protection. And finally, we made an indicator related to landscape aesthetics. And in this case, it was coming from the perspective that a lot of people quite like to see a big view, and the types of ecosystems that they can see within that view has some bearing on the quality of the aesthetic experience for them. So this was the set of the models that we developed. I just want to say that these are all completely or mostly not something that has come from scratch, but they are somehow building on a longer history of development in how you should go about modeling these ecosystem services, either developed at Manaki Whenua or often in other places around the world. So we leaned on a whole variety of existing research and existing models that are out there and published and often validated as well. Quite a famous one is this INVEST, which is coming from Stanford University. iTree is a mainly urban forest ecosystem service set of models. The ones that we've incorporated here are the ones for air pollution removal and UV protection. Carbon stock is coming from the literature on allometric equations and parameterized from some studies in New Zealand. The curve number approach is quite a old and standard method coming from civil engineering, which is used for runoff retention modeling. For shade, we used a similar approach to the nice maps Jan just showed, where we're ray tracing solar rays and seeing what they bounce off of. And the landscape aesthetics is an idea that came from our collaborators in France at CNRS, and we have also continued developing. So the point is to say that there is some some scientific basis in the software package, and all of this is referenced in the documentation appropriately. They have also all, with the exception of the UV protection model, they've all been applied before in different parts of New Zealand at different times. The UV protection one was actually just a little aside. It's really cool to be able to incorporate this. We haven't used it before. It's a model that was developed first in Korea and is incorporated in the US iTree program, but it's the first time within this partnership program project was the first time that we've had the opportunity to incorporate it and parameterize it for New Zealand. But all the others have been used before, maybe not validated, but there is at least a precedent for using them and developing the most appropriate parameters to use inside them for New Zealand ecosystems. The data fusion, a bit of it is maybe upselling it a little bit too much, but the idea is that in addition to the new LiDAR project provided data layers that we've heard about already, some of these models also require other information, and so it's about putting together a suite of data sets that allows us to best parameterize the models with the best available and comparable information that's available at the moment. An example of this, for example, here we have two different maps that in some way represent the land cover of the environment. Here we have LCDB at the top, which is great because it has such a variety of different vegetation types within it. Each of the numbers here corresponds to a class within LCDB. But you can see it's quite a relatively coarse resolution in comparison to the tree canopy cover map here, which is at a finer resolution, but in this case only has one type of vegetation cover, which is trees or not trees. So we had to think of some ways to try to incorporate these two together to get the best of both worlds. We want the high spatial resolution, but we also want the level of detail in vegetation types. So to do that, we assume that we built a kind of statistical model saying that in every part of the map here, there is a most likely kind of woody vegetation, and we overlay this with the tree canopy cover map and extract it so that here we have the combined map where the non-tree patches of the vegetation are at the low resolution of the LCDB, but the tree areas of the map are at the high resolution of the LiDAR product, but also incorporate information on which LCDB class are they most likely to be. So the main output, as I said, was this R package. The general principles underneath it are that we would create one R function per different model that you could call. It's intended to be somehow universal internally. So, for example, a lot of the functions require a land cover map. And so across the different functions, we try to keep that in the same place and make sure that the type of data that's required is standardized and so on. And these are universal models, so they are generally applicable. And within the scope of this project, we have customized them for Hawke's Bay, but they could equally be customized for another region of interest, mostly within New Zealand, but also outside perhaps. So none of the like important or influential parameters are hard coded. You have to add them in every time, but there are some defaults. Particularly, there are some defaults for Hawke's Bay. We tried to make it as independent as possible and not depend too much on other packages, though there have been some hiccups along the way that we're still trying to iron out, where some things that we did depend on have stopped being updated or used. And it's meant to be easy-ish to use, and I don't mean that in the sense that it's actually easy to use, but it should be easy to use if you are familiar with using spatial data within R. So it's kind of follows the general way that things are done in R and for spatial analysis. So the package is available on the Manaki Whenua GitHub site right now, so you can download it and install it into your own version of R. This is the website. There's a link included there as well. Also, alongside the package, you don't just get the code, but you get some other information. So, there's a little guide on how to install it, for example. And this is from the website directly. It tells you that there's also a small tutorial and the documentation, which I will continue to go through a little bit now. So there is this documentation which I wrote, which explains how the models work in a little bit more detail and provides the references for them. And also it has this kind of guide where we run through each of the models that are currently included in the package, and you can test out the function there. Once you're inside R, this is R Studio in case you haven't used it, but you can also access the help at any time. So here I've queried the help for the shade model, and it provides it provides you with a description of what the function does, and it tells you the main parameters that you need in order to call the model, which in this case are a land cover map, a canopy height model, a cutoff value for the height of the people that you want to model shade for, and then some other ones about improving the efficiency and downscaling. You need a digital surface model, and you need to know where the sun is when you are calling the model at that time. So all of the functions have the same help page. Further down the page, there's a little example of how to use it as well. Also included in the package is this really tiny 500 meter by 1 kilometer test region, which is from within Hawke's Bay, and it includes a series of data layers so that once you install the package, you don't have to go hunting around for data in order to learn how to use it. You can instantly use these data layers within the tutorial. One example of a model that's included is two, for runoff retained by ecosystems. Runoff retention is important because it relates to flood risk. And we follow quite a standard approach for doing this, which is called the curve number approach, which is really quite an old approach, but there are several different versions of it. So to give some example, this is directly from the tutorial in the documentation. So here we are providing the code and we are providing the HBRC runoff curve number model with the required information that it needs, which includes various layers for land cover and hydrological soil group maps, and also the precipitation. In this case, we're going to put in 90 millimeters over a day, and also whether the current conditions in the catchment are average, dry, or saturated. So in this example, we come up with a map that provides a map of which areas of the test area are retaining more or less of that incoming rainfall. So higher value means that a higher value means that a higher proportion of the runoff is being retained. There are some artifacts which are partly by design to explain things in the tutorial. You can see this big rectangle here of coarse resolution. This comes from the very coarse resolution data of the hydrological soil group map that we provided with it with. So it just gives a discussion about you can have very high resolution data in some data sets and lower resolution in other data sets, and that will influence the look and the total values of the outputs that you come up with. And we also compared another version of the curve number approach, which is recommended by MB down here. That one's quite cool because it also incorporates slope. So a shade example, this is the shade model running. The thing about shade, when we think about it from the ecosystem service perspective, is that we don't just want to know which areas of the landscape have more or less shade, but we need to understand what the contribution of the vegetation is in providing that. So typically we run several versions of a mechanistic shade model, sometimes including the vegetation alongside other things that provide shade like hills and buildings, and sometimes excluding them. And so that gives us a map here of the proportion of the time that different parts of the landscape are shaded. And on the right here, we have the proportion of shade provision that is attributable to vegetation. There are a few other things that are included in the documentation document. One is a discussion about uncertainty and an example for how to, if not accommodate that, at least describe it. So the problem with ecosystem service modeling is that they involve a lot of parameters for different things, and often the output that you get can be quite sensitive to the choices you make about parameterization. So in the example of air pollution removal by leaves, a really important parameter is the deposition velocity, which is how quickly particles of particulate matter attach to leaves. And this is a long debated parameter, and it's something that's quite hard to measure in the lab, let alone in the field. So typically the literature uses this value of 0.0064 meters a second, but there have been a load of other studies that show that it depends a lot on pure chance, but also things like the species of trees that we're dealing with. And so, for example, you can see from this other article, there's quite a big range in possible values given here. So in the documentation for the package, we talk about this problem and explained an approach for propagating this uncertainty so that we can not only give one estimate of the benefits of nature for our case study area, but also put some kind of confidence intervals on what that might be. So here's a bit of code which is included in the documentation for running an uncertainty or kind of sensitivity analysis about that. And over here we have the eventual confidence intervals in a day. Our section of the map is removing about 10.9 kilograms of particulate matter, and we have this quite big 95% confidence interval ranging from about 5 to about 15. So yeah, uncertainty is still present in this kind of modeling, but it's more important that we try to characterize and explain that uncertainty to people, I think, rather than just ignoring it, as is often done in the past. We also did run all of the models for a subsection of the map around Wairoa. Here are some of them to give some idea of the kind of outputs and resolutions that can be expected. So here we have again the runoff retention mapping that I showed the more detailed example for. And again, you can see these artifacts of the low resolution soil classification map underneath in there. But also there are more detailed patterns where we have trees or not trees and things like that. This is the UV protection model, which is an indicator equivalent to the SPF factor on your sun cream. So areas of the map that have a UV protection factor of 100, you would take 100 times longer to be sunburnt there than areas where it's 1. It's quite a coarse resolution model, and it relies on having tree canopy cover. So unfortunately, this map isn't particularly interesting. And here we have the results of the shade vegetation contribution, where we can pick up things like the shade provided by shelter belts and so on. So that, yeah, I mean, unfortunately, an R package is quite a dry thing to give a presentation about. I thought it would be good to show some applications of this kind of ecosystem service model that we've worked on elsewhere. Here is a paper and a web map that we put together, where this actually preceded the development of the HBRC package, but some of the ecosystem service maps that are provided on this website were developed using comparable approaches. Some of them we've improved upon a little bit. So, yep, you can explore all the different layers of information there. More recently, we had some work with Selwyn District Council and mapping, again, the same set of ecosystem services as are included in the package for Rolleston. And they have just a couple of weeks ago published this nice website which explains the importance of ecosystem services and how they want to use this kind of information in their regional planning. And so they also have some other maps. Here's the UV protection factor map that's available on their website. Oh, and also by putting together this information with other data sets like the New Zealand Garden Bird Survey, we can also create maps, for example, of species richness, which is important ecologically, but also because people like to see birds in their gardens and so on. So yeah, thanks very much. Yeah, it was really fun. I really enjoyed working with Kathleen, and thanks to Manaki Whenua and Hawke's Bay for funding. Thanks.
Awesome. Thank you for making a very R package heavy talk, quite visual and lots of examples. Really great. There aren't any questions in the chat at the moment. I was interested because you've obviously worked quite closely with Hawke's Bay Regional Council. How this might inform, what kind of decision making these types of maps that you can produce might have come up in discussions that it might inform.
Yeah, I think one was related to the runoff retention, for example. Kathleen asked if we could run it several times, I think, for different. You can put in different amounts of precipitation, and you can also define whether the ground is already saturated. So that kind of scenario understanding, I think, is one use.
Awesome.